Okay, so I thought that Calc 2 students might be able to use another example from 9.9. So this is for the assignment that includes some stuff from 9.7 and then also some stuff from 9.9. So we're using, in both these sections, Taylor series or power series to approximate functions, to come up with ways to express functions. So quite an interesting topic. Anyway, so the last example we're going to do in section 9.9 has to do with using integration of a power series. This kind of brings together all the stuff that you've done in section 9.9, and then it's got a little bit of history with it too, which I really like. Anyway, so we're supposed to find a power series to represent arctangent of x and to represent it at 0. So this is like a very historical problem because it has to do with the ways that people in the past were able to approximate pi to a lot of accuracy. So it's a very historical problem, if you will. Anyway, so we know that the derivative of arctangent is 1 plus 1 over x squared. So that's going to be key for this whole thing. So the idea starts out by saying, hey, can we develop a power series to represent the function 1 plus 1 over x? And I think we did that, right? If we remember that geometric series can be represented as a times a over 1 minus r, geometric series converge to that if they do indeed converge, if they have appropriate radius of convergence, then this thing, remember, is pretty easy to manipulate into that form. We just say that replace r with negative x, right? If you go 1 minus a negative x, you get 1 plus x. There you go. So the a is 1, so you've got an implicit 1 here. And then negative x to the n, if you go negative x to the n, remember that's going to be negative 1 to the n, there you go, and x to the n. So there you go. This guy can be written as this series, and its interval of convergence is going to be negative 1 to 1. So not a fantastic interval of convergence, but it is centered at 0 like we wanted, right? But you're saying, hey, I thought we needed to do something with 1 plus 1 over x squared. So we say, all right, let's just replace that. This is a function composition, right? So this is really, really neat. You can plug in x squared to that function we just developed a power series for, and it goes right here, right? Just using function composition. So then the only question is, how do we plug x squared into a function? Well, didn't we just learn about operations with power series? So here's another reason, like on the previous um, in previous stuff that we did, didn't we know that the operation of plugging x to some power into a power series, that became the series, oh my gosh, that doesn't even look like a series, my bad. If that became the series, whatever a sub n was already there, and then you went power to power, so now it's like x to the n as it was, and then power to power is multiply, right? So you multiply that factor in that you had. So we had an x squared factor that we wanted to do. So instead of just x to the n from up here, now we've got x to the 2 times n for that 2 times that n. So that's why we needed operations on power series for stuff like that. Anyway, then we say, all right, so this isn't arctangent, right? But if we integrate this, it is arctangent. So in other words, what we're going to basically do is integrate this guy to obtain arctangent on both sides. So if we integrate the power series, we learned how to integrate power series too, right? The only x here is x to the 2n, so integrate that, go 2n plus 1, divide by 2n plus 1, and you get some constant as well. And then that's going to be equal to the arctangent of x. So a pretty neat move there. It says let x equal 0, then c equals 0. So basically, you get that that constant goes away. It's not necessary. And there you go. There's the power series that represents arctangent of x. If you expand it out a few terms, it's a really simple looking series. It's x and then minus x cubed over 3, and then plus, so it's an alternating series. But it's a pretty simple formulation. So I think that this was developed way back in the 1600s. That was developed way back in the 1600s by a guy named James Gregory, who had a lot to do with series. So it's crazy that this has been around for so long. And one of the things it was first used for is getting a nice value of pi. That's obviously very important to mathematics for all kinds of reasons. So people said if you use that series on the arctangent of 1, we all know that the arctangent of 1 is pi over 4, right? The angle whose value has a tangent of 1 is that 45 degrees guy that is, pi over 4. So then you just multiply that by 4, and you've got a nice approximation for pi. It just depends how many terms you carry this series out to. So this is one of the first ways that pi was really accurately produced, but it was really expensive. What do I mean expensive? It says it converges very slowly. You needed hundreds of terms for reasonable accuracy, so let's just see what we've got right there. If we just do that many terms, we get 1 minus 1 divided by 3, plus 1 divided by 5, minus 1 divided by 7. So far, those first 4 terms are only 0.7238 about. Pi over 4 is 0.785, so that's really a rough approximation. So apparently, even though this was a really accurate way to do it, you needed so many terms that it wasn't very practical. So we're going to look in a second here another way to do this, which was invented only about 40 years later, and it only needed a few terms to develop pi. It was really clever. In fact, let's just go look at that right now. So this was a really clever way to do it, and it only needed a few terms. So it uses a trigonometric identity for arctangent. This is probably a more obscure one that you're not familiar with. But anyway, so you can use this identity with arctangent, and then each one of these guys, you can use that power series that we just developed and plug in 1/5 and plug in 1 divided by 239. This was done in 1706, right? So it's pretty crazy that people had to do that kind of multiplication back then without calculators. But anyway, you multiply that by 4 and you get a really decent value of pi. It's got an error that's in the 10 to the negative 7th range. I mean, that's really great for when you didn't have computers. So people were coming up with this stuff a long time ago. One of the most amazing figures is this guy named Ramanujan, who back in about 1914 he came up with all kinds of devastatingly new mathematics, which is still being only understood today. It was so advanced for its time. And what he did is he approximated pi each term that you added. So in other words, like adding one more term to the series that he created. And we're not going to look at that series. It's just too complex at the moment. But one more term added 8 correct digits to the value of 1 over pi. So then you used the reciprocal and you had pi. So that's just incredibly amazing. So computers nowadays use things like the stuff that was developed by Ramanujan because it's just so devastatingly efficient. Anyway, the reason we looked at this is just as a hint. Let me look here. So in your assignment, let's see, on page 675, the directions say on 53, find the sum of the convergent series by using a well-known function. So I think the well-known function you might use, one of them, on a couple of those problems, you might be using the arctangent series, which is well-known, obviously, because of its relationship to this approximating pi thing in history. There might be another couple well-known ones from the chapter, like 1 over 1 minus x. That's, of course, very well-known. That's just the series x to the n, right? So that's the kind of thing you're going to use on those problems. Okay, see you next time.